Welcome. So this episode is going to be about something which you may have some interest in, which is how we make decisions about the quality of visualizations. How do we decide whether a visualization is good or bad quality? So in this course and similar courses, we have summative work, which is work that is marked, and along with that mark is some feedback. And most courses like this are designed in this three-stage process where there's something that's called presage, which is the background that you've got and the background the course brings in, the set of learning outcomes for a course. There's a process, which is the teaching and the support in seminars and laboratories and online with human feedback. And there's the product with the outcome, which is hopefully you, which you've learned something, and a piece of work which you demonstrate that in, which we mark and we provide feedback on. So this is known as the 3P model. It's fairly standard in educational theory. Beeks discussed it in 1999. It's a very simple model, but it's quite useful for thinking about how to design courses. When it comes to automating assessment, so summative assessment, there are a range of challenges in making an academic judgment on summative work. In visualization, we need to define a set of principles that we want to teach and mark against. That's not as easy as you'd think because there's not a well-founded piece of theory that goes back hundreds of years in visualization. It's a relatively new field, but we have an idea in the marking schemes we give out for that. We need to consider bias as a prejudice. It's usually designed as a set point in a system, but bias in a negative way suggests that somehow we'll be biased against different people in different ways. There's also noise. So in his recent book called Noise, Daniel Kahneman suggests this is often a much bigger problem than bias. So it's not so much that the marking is biased, it's just that there's a random noise added on top of it, which makes different marks different. So we want to try and help overcome bias and noise and be more evidence-based in marking and feedback. And that led us to think about how can we do automatic assessment that can help with at least the last three of these challenges. There's a paper by Wilcox, about 2015, that talks about if you're going to automate assessment, you need to suggest that it contributes to the learning and that its benefits outweigh the costs. Automating things like assessment is expensive, and as the A-level results found out last year, can often go very badly wrong. Here's an example from a summative exercise last year. It was the data from the Manchester infection outbreak, and the idea was to try and produce a visualization that enabled people to zoom in on the most impacted, highest certainty areas of the visualization. This shows the whole area affected, and this shows one such visualization zoomed in. So you can select here on the left the level of impact you want to look at, the highest impact, and the level of certainty, the highest certainty areas as well. So how can we go about trying to automate the visualization of this? Well, we can use some image processing tools to start to help us. The set of learning objectives we're going to use those tools to try and help with are these. Does the visualization fit the task? Does it use visual channels well to represent data values? So shape, brightness, transparency, size, and color. Does it use Gestalt principles well? Does it lay out proximity well, grouping similar things together? Does it use contrast, repetition, and alignment well? Is color used? Is it compatible with people with different color vision abilities? And will it work well if it's printed out in black and white? And does it match certain other metrics that we have as well? Interaction is a tough one to judge because, in fact, we'll be judging still images. And so is technical aspects, reliability and size and readability we don't do too much with. But you can use some of the tools to help judge if the language is readable. So is it visible? Is it at a level which is not faded into the background, at a level of contrast which isn't faded into the background? So here's one metric that we use, edge congestion. This is a metric that proposed by Rosenholz and Nakano, and it looks at areas where there are lots of edges in an edge analysis of the visualization. So it's not just the edges, it's where there are many edges nearby. And it's been correlated with perceived image complexity and also with aesthetic quality. So higher complexity is usually a bad thing. It makes it more difficult to detect signal from noise. and aesthetic quality, more complex visualizations tend to be rated lower aesthetic quality. You'll see here this particular visualization was just slightly above the average in edge congestion, but roughly in the right area. The blue bars represent all the data previously seen by this software tool. Saliency is a judgment on the visibility of items in the picture. So this is there's a range of algorithms which can do this. This one uses an algorithm by Itti and Koch, and we also use a low detail algorithm in OpenCV, and we tested a neural network, but it was a lot slower and no better than the other two so far for this application. In judging visualization quality, saliency helps us see which things stand out the most. You'll see here that in the ranking table on the right, the plot, this particular image has quite low saliency, so it's probably not such a good thing. It's just the contrast could be improved. And also, if you look at the image, the highest contrast item in this image is the little color bar in the bottom left of the image. That's not great because that means that the data itself isn't the thing that will attract your attention first. We're also able to use tools to simulate different abilities of color vision, and this simulates 3 different degradations of color vision: deuteranomaly, protanomaly, and tritanomaly, and also monochrome, so it will print out in monochrome. And one of the things in this visualization I'll pick up on is that in the key again, the very high and very low colors, because it's diverging on a diverging scale, when you print it in black and white, they both end up at black. So you can't tell the difference between very high and very low values here. Luckily, the data here is in the mid-range, but it is a flaw in many visualizations, and some of the government's visualizations on COVID have exactly this problem. These are 2 other metrics that we use. The wave metric, which judges color preference. This particular one is slightly low on color preference. And the other metric we use, Hassler-Sustrunk, is a metric that judges color fullness. So this means that across a range, it will tell you how colorful an image is. And typically people prefer high colorfulness images. So they like the aesthetic impression of high colorfulness. And it might not be surprising, but the image we're just testing here has relatively low ranking on that colorfulness scale. So we use these automated metrics in the marking and feedback process. We don't use them to generate the mark, but we do use them to generate feedback, and we're going to use them in this course. Here, a student sends in a submission, we take a snapshot of it, we send it through the automated metrics, and they feed information into a database, which is stored for future assessment tests, and also into a report. Those images and that data are used by the human assessor to write marks and written feedback, and that's fed back again into a report. And for this single image, we'll generate a 9-page report on both from the human viewpoint and from the machine viewpoint. So this is teaming human and machine judgments on something. And the benefit here is that the machine's giving us a very clear evidence in some areas about what is and isn't working. The feedback report in this course, we sent to each student a feedback report against each of the learning outcomes, some notes in note form, some marks which are deleted here, and then these are the first 2 pages of the report. The remaining 7 pages were the automated feedback from the machine and some information on how to interpret each of the sets of automated feedback. If we look back on learning objectives, where does the automated analysis most help? It's not a huge help in fit to task or in the technical aspects or in the use of interaction, but it does help provide evidence towards what visual channels were used, how well Gestalt principles were used. It happens to be really quite easy to see layout in the saliency and edge congestion images. And it definitely helps with color, so it will help tell us whether or not different visualizations will work with different color abilities. And the wave and the Hassler-Sustrunk metrics help us give feedback on the image aesthetics in color. Language and text, actually, the saliency and edge congestion can show us if the language and text is standing out, and if it's standing out much more than the data, which is probably not a good thing. It also helps judge if it's a little bit too small. Then it comes on to thinking about, well, okay, we're doing these visualizations in a marking context. We've got to think about ethics, trust, and privacy. So this work wasn't about grading student work, but it is about helping support feedback for students. And there are 3 areas where we need to be careful. One is to build trust, so we try and In the feedback, we describe the algorithms, so you can easily see how you can look up, if you wish to, what the algorithms are doing to the visualization to generate the feedback. We have to look also at ethics and privacy. The work we've talked about here, we've got permission to show you. We don't normally have that, so we'll ask people whether or not they'll let us talk about their work. One of the upcoming problems for this type of algorithmic assessment of work is that the EU is proposing to ban it unless you go through a set of rigorous testing. So it'll be rated as a high-risk algorithm alongside face detection, for example, which in fact is outlawed, and some other high-risk algorithms. It's certainly unclear if human-machine teaming presented here will be allowed in the EU without formal verification of some kind. So I'm going to say the marking process feels better evidence to me than it did before we started using this work. Student feedback and the feedback from the course external examiner was positive generally. They said it was interesting and useful to understand something more about their visualizations. And benefits and costs is harder to judge. It's been quite a significant effort to produce the software, even reusing something called AIM code, which we'll demonstrate in a minute. But it may start to pay off from now on, where we've got the code to reuse each year. It does help separate concerns so that the system benefits from human and machine strengths, so that, for example, when I'm marking, I no longer rely on my own judgment on the colour vision. I use the colour vision simulations. That does mean that we need to be careful to be sure that they're working. Thank you. That's the end of this episode.